All right, welcome everyone this morning. Our webinar, introduce Bill Lamberson from CIRES and the Weather Prediction Center. And Bill is going to be presenting on the use of multimodel ensemble clustering to improve precipitation at WPC. Pass it on to Bill.
Thank you, Jeff. So I'm just going to start with a little bit of background and motivation about WPC and our mission, which is to provide national forecasts and situational awareness for hazardous weather events with a focus on those associated with heavy precipitation. So going forward, the National Blend of Models, or the NBM, will be the starting point for NWS precipitation forecasts, with WPC making targeted changes to the NBM in consultation with the RFCs and the WFOs. So what is the NBM? So the NBM is a nationally consistent and skillful suite of calibrated forecast guidance based on a blend of both NWS and non-NWS numerical weather prediction model data and post-processed model guidance. So the goal of the NBM is to create a highly accurate, skillful, and consistent starting point for NWS gridded forecasts. And at shorter lead times, say days 1 to 2, the NBM forecast is dominated by short-term high-resolution guidance. But as you go further out in time, so day 3 and beyond, the NBM forecast becomes dominated by the global ensembles. And just as an example, I have here the 24-hour NBM forecast for precipitation for Hurricane Ida, and this forecast was made about 3 or 4 days prior to the event. So the meteorological problem. So the NBM does a good job of blending a large volume of forecast data into an accurate and actionable forecast, but it's sort of a black box. Forecasters crave more information on what went into the NBM forecast, and they also want information on forecast uncertainty in space and time that the NBM doesn't necessarily provide, and they need tools that will give them this information. So just to kind of illustrate this, I have some of the NBM percentile forecasts for Hurricane Ida's rainfall. So we have the 25th, the 50th, the 75th, and the 90th percentiles. So on all 4 of those plots, I have 2 black dots. One is showing the location of Columbus, Ohio, and the other is showing the location of Scranton, Pennsylvania. And if we look at the 4 percentile forecasts for those 2 locations, they're almost identical. However, we as meteorologists know, and just by looking at some of the forecast data, that the scenario where Scranton realizes the 90th percentile forecast is probably not the same scenario where Columbus, Ohio realizes the 90th percentile NBM forecast. But you have no way of knowing that by looking at these NBM percentile plots. So the impractical solution would be to look at all ensemble members. And just to illustrate that, I have a plot of all 100 global ensemble members that go into the NBM. So we have the European with 50 members, the GEFs with 30 members, and the Canadian with 20 members. Obviously, looking at this is very impractical with forecasters working under kind of strict time constraints. If you just glance at this, you can see there's a lot of colors. And so there's probably a heavy precipitation event that's going to occur, but it's really hard to see, what are the dominant forecast scenarios and where's like the most likely area to get the heaviest rainfall. So the overly simple solution is to calculate ensemble means for each ensemble prediction system and kind of treat them as the possible forecast scenarios. So there are benefits to this. It's very simple and lets forecasters somewhat see the underlying data that went into the NBM, but there are also some drawbacks. It doesn't adequately show the range of possible forecast outcomes, and it assumes that the biggest determinant of an ensemble member's forecast is its parent model, which isn't necessarily a valid assumption. So again, we can see the 3 ensemble means from the Canadian, the GEFs, and the European ensemble, and there is some sort of variability between them, but obviously there could be a lot more within model variability that isn't being captured when we're just looking at the mean. So what's a better solution? A better solution is ensemble clustering. So ensemble clustering partitions the members of an ensemble into groups of members that have similar forecasts, or in other words, discrete forecast scenarios. And simplifying the ensemble down into a few clusters allows forecasters to dig more into the data and get more complete information about forecast uncertainty in both space and time without that data overload problem. So to assist WPC forecasters in their creation of medium range day 3 to 7 precipitation forecasts, WPC is developing an ensemble clustering tool specifically for QPF that will align with WPC's workflow and forecast responsibilities. So ensemble clustering, so how do you go about doing that? So WPC's QPF clustering tool will use a version of ensemble clustering known as fuzzy clustering. And there are basically 3 steps in fuzzy clustering. The first is to evaluate and interpret the first 2 empirical orthogonal functions, or EOFs, of a relevant ensemble forecast variable over a region of interest. The second is to use k-means clustering on the principal components, or PCs, for the EOFs to create clusters of similar members. And then finally, the third and most important step is just to view the clusters. So these are the specifics of WPC's fuzzy clustering method. And some of these have changed, and I'll go over the changes more towards the end of the PowerPoint. But this is just what we were using when we were doing a lot of development work, and what I will be using for this case of Hurricane Ida to kind of illustrate things. So the ensemble data set that we're using is half-degree resolution versions of the global ensembles, which is again the Canadian, the GEFS, and the European ensemble. The relevant variable for EOF analysis is 24-hour QPF. The regions of interest are 6 regional domains over the CONUS, so the Northeast, Southeast, North Central, South Central, and Northwest and Southwest. And then how many clusters should we have? Well, generally 3 to 5 is a good number. And so what we do is we run k-means on the EOF PCs with 3, 4, and 5 clusters. And then we use the silhouette scores to determine what is the optimal number of clusters. And again, I have optimal in quotes because that can kind of be a little subjective. So for example, let's just apply fuzzy clustering to the 4-day forecast for Ida's rainfall over the northeastern United States. So just to refresh your memories, although most people probably remember, here is the 24-hour QPF, or I should say QPE from CCPA, for Hurricane Ida, ending the 24 hours 0Z on Thursday, September 2nd, 2021. So obviously, there was additional heavy rainfall that fell on the next day, particularly in the New York City and New England areas that caused a lot of flooding. But for now, we're just going to focus on the 24-hour period ending 0Z on Thursday, September 2nd, which also had a lot of heavy precipitation, just located a little bit further west over Pennsylvania and the Mid-Atlantic states. And again, I've highlighted the 2 black dots. One is the location of Columbus, Ohio, and one is the location of Scranton, Pennsylvania. And you can see, indeed, Scranton did get close to realizing that NBM 90th percentile, but Columbus basically came nowhere near that. All right, so step 1 is calculate and interpret the first 2 EOFs. So a note on EOFs. Basically, they're a data analysis technique often used in climate studies as a method for determining the spatial patterns that most efficiently explain the variability of a multivariate data set. So in other words, what patterns are most common in the data set. And it's how we get teleconnections like the NAO. So for example, the NAO is just the first EOF of the sea level pressure field over the North Atlantic. However, EOFs that are calculated across the model ensemble member dimension as opposed to that more conventional time dimension result in modes that show the dominant patterns of differences between the individual ensemble members and the ensemble mean. And for each EOF, each ensemble member will have a principal component, also abbreviated as PC. So a note on PCs, the PCs are the projections of the dominant EOF patterns onto the difference between each of the ensemble members and the ensemble mean. So just an English translation, an ensemble member with a large PC for an EOF pattern will resemble the ensemble mean with that EOF pattern added or subtracted to it. And whether you add or subtract to it depends on the sign of the principal component. So for a positive principal component, you would add to that EOF, you would add the EOF pattern to the ensemble mean. For a negative principal component, you would subtract that EOF pattern from the ensemble mean. So again, it's a lot of math, but you don't need to know the math in order to interpret and apply the results of the EOF analysis. All right, so we're going to be calculating the EOFs of the 24-hour QPF field over the northeastern US on day 4, which we're defining as 0Z on September 1st to 0Z on September 2nd, from the global forecasts initialized at 0Z on the 28th of August. All right, so on this slide, we do have those 2 EOF patterns. So on the figure on the left, we have the EOF1, so the leading principal or the leading EOF, and on the right here we have the second EOF. So in both of these plots, what is contoured here is the multimodel ensemble mean field, and then the shading is the actual EOF pattern. And also on the upper right here, it tells you how much variance in the ensemble that is explained by this EOF. So for this first EOF, we explained 25% of the variance. And for the second EOF, we're explaining about 16% of the variance. So again, the EOF show the dominant modes of variability in the ensemble forecast. If we look more closely at EOF1, we can see that it's a dipole that's kind of located along that axis of heaviest precipitation, with heavier values over Pennsylvania and lower values over the Ohio River Valley. So basically what this is telling us is that there is considerable uncertainty in the timing of the precipitation. Because remember, if an ensemble member has a positive principal component, we're basically adding this EOF pattern to the ensemble mean, which would result in heavier precipitation over Pennsylvania, less precipitation over the Ohio River Valley. And conversely, if we have an ensemble member with a negative principal component, we're subtracting this. So lower precipitation over Pennsylvania, higher precipitation over the Ohio River Valley. And since that's basically along the track of heavy rainfall from Hurricane Ida, basically this is telling us there's uncertainty in the along track, which is another way of saying differences in the timing. So looking at EOF2, we also see a dipole, but this time it's kind of across the track of the heaviest precipitation of Hurricane Ida. So what this is telling us is that there is also uncertainty in the north-south position of the heaviest rainfall. All right, so as I've said, all the ensemble members will have a principal component for EOF1 and EOF2 that will kind of tell you how that member relates to those EOF patterns. So what you can do is you can plot all the ensemble members in a phase space with their principal component for EOF1 along the x-axis and their principal component for EOF2 along the y-axis. Now, I've kind of already gone through and clustered them, but just ignore that for now. But we can see all 100 ensemble members are plotted in this PC1, PC2 phase space, with the European ensemble members in the blue, the GEFs in the green, and the Canadian in the red. Now, I've also gone through and kind of put the physical interpretation for what each area of the phase space represents. So again, those ensemble members that have a principal component for EOF1, that's positive. So the ensemble members in this area of the phase space will have an IDA that's moving a bit faster. The ensemble members with a negative principal component for EOF1, so again, subtracting this from the ensemble mean, have that Hurricane Ida or the remnants of Hurricane Ida being slower. For EOF2, the ensemble members with negative principal components for this EOF are basically have IDA displaced further to the north, and the members with the principal components that are positive for EOF2 have IDA located further to the south. So that's sort of basically how you go through and kind of find out the physical interpretation for each of the areas of the phase space. Okay, so next we're going to go through and actually cluster. So a note on k-means clustering. It's an algorithm that groups two-dimensional data to minimize distance between each point and the center of the cluster it is assigned to. So the number of clusters needs to be specified beforehand, and usually 3 to 5 clusters is appropriate. So again, to select the optimal number of clusters, we run k-means clustering on the EOF PCs to create 3, 4, and 5 clusters. And then the number of clusters that produces the highest average silhouette score is selected. And again, the silhouette score is just kind of a measure of how similar an object is to its own cluster versus the other clusters, and generally a higher score is better. And again, what is optimal is a bit subjective, but we needed a way to objectively come up with the number of clusters, so we settled on using the silhouette score. All right, so now I've gone through and done k-means clustering on this phase space, and it's come up with 3 clusters. So we can see cluster 1, the main thing that they have in common is that they're inhabiting this area of the phase space. So the main thing that they have in common is that their principal component for EOF1 is negative. So basically the physical interpretation for cluster 1 is that IDA is slower than the multimodal mean. Looking at cluster 2, they inhabit this upper area of the phase space with principal component for EOF1 that is positive and for EOF2 that is positive. So the physical interpretation for cluster 2 is that IDA is faster and further south than the multimodal mean. And then finally, looking at cluster 3, It's down in this bottom part of the phase space. So the physical interpretation is that IDA is faster and further north than the multimodel mean. All right, so obviously going through those EOFs in the phase space can be kind of complicated to come up with the physical interpretation of each cluster. But honestly, you can skip that if you want to and just look at the actual clusters, because what the physical interpretation is will become readily apparent when you actually look at the forecasts. And that's what we have here. So we have the 3 cluster forecasts as well as the verifying QPF analysis. So looking at cluster 1, that was that cluster that had IDA slower. And if you look at the actual QPF field, you can see that it has most of the heavy precipitation held back and over Kentucky, Tennessee, and the Ohio River Valley. Now, for each of these 3 cluster plots, the top here kind of shows this relative support among the various ensemble members. So for here, we have 3 Canadian ensemble members, which is 15% of the Canadian ensemble, 17 guest members, which is 57% of the guest ensemble, and 42 European ensemble members, which is 84% of the European ensemble, for a total of 62 members, or 62%. So at the time, this was the most favored solution. However, since we have something like the clustering product, we can see some of the other solutions that maybe were less likely, but still plausible. So if we look at cluster 2, that was with IDA faster and further to the south. And looking at the QPF field, you can clearly see that it's much faster than this solution, but a bit further to the south than, say, cluster 3, which is also faster, but further to the north. And actually, in this case, looking at the verifying analysis, you can see that cluster 2 ended up doing a good job. And even though it only had 22% of the ensemble, so again, maybe not the most likely solution, it was still plausible, and a forecaster would be, well advised to be aware of it. All right, so putting it all together. So the EOFs of 24-hour QPF show the dominant modes of uncertainty in IDA's rainfall forecast. A forecaster coming into work 4 days prior to IDA could view the 24-hour QPF EOFs and immediately see that the greatest uncertainty in the forecast was the timing of the system, with the north-south location of the axis of heaviest rainfall being a secondary area of uncertainty. So the clusters based on the QPF EOFs do a better job of showing the possible forecast scenarios and the relative likelihood than currently used ensemble visualization techniques. And this is useful information when making and communicating a forecast and the possible ways it could play out. So now I'm just going to go over the summary and future work. And this was summary and future work at the time. And then we're going to go into some of the future work that I've done since I originally gave this presentation at AMS a few months ago. So again, the summary is that WPC is developing a QPF ensemble clustering tool to help forecasters dig into the data that's underlying the NBM forecast to better visualize forecast uncertainty and potential forecast scenarios. So one of the big things we wanted to get was to obtain NBM's bias-corrected and downscaled versions of the global ensembles and use them as the base for the tool, because then we would be directly using what's actually going into the NBM. Another thing we wanted to do was to perform clustering on discrete QPF objects instead of QPF over arbitrary regional domains, because obviously heavy precipitation events can span multiple regions, and it was just kind of awkward to have to look at 2 sets of clusters for one, continuous QPF field that just happened to straddle 2 regions. Another thing we wanted to do was to add clustering on 48-hour QPF to account for multi-day events. So again, same thing. Obviously, heavy rainfall events can span multiple days, and it was just kind of awkward to have to look at 2 sets of clusters for, one half of an event versus the other half of the event. And then finally, we wanted to host this tool on a publicly accessible website. All right, so obtaining the NMQMD ensemble members. So MDL starts with the half-degree resolution global ensembles and then performs a quantile mapping and dressing techniques to all 100 ensemble member forecasts of QPF before incorporating them into the blend. So before we were just using the raw half-degree data, but obviously MDL, they have much more computational power and they can do a lot more with the raw data than we ever could. So essentially what this QMD technique is it's a bias correction and downscaling techniques. And for NBM version 4.1, the supplemental locations have been eliminated from the QMD technique. And this is the version that we will be using because this was the version that they were kind enough to share with us. So now that we can cluster directly on the ensemble QPF that is going into the blend instead of a coarser resolution. So to kind of demonstrate this, I have the raw QPF versus the QMD QPF, and this is for a case that we're going to be looking at. This was a 48-hour case ending at 12Z on the 5th of February. We only got access to this data set at the end of January, so we haven't had a ton of time to look at this and kind of do a lot of case analysis. But on the left here, we have the raw QPF ensemble mean from the 100-member ensemble. Again, this is just that raw half-degree ensemble data. So it's pretty coarse in resolution, but it does a decent job. And then on the right here, we have the NMQMD QPF. So again, this is the mean of 100 ensemble members, but this is after MDL has done their QMD technique on the QPF field for each ensemble member individually. So just comparing the two, you can see it definitely increases the amount, especially over the southeast, which is generally a good thing because a lot of the heavy precipitation events in the southeast are more convectively driven, so you can get a lot of very heavy rainfall over a short period of time. But also you can see some sort of terrain details. I mean, obviously the east doesn't have the terrain of the west, but you can see there's a little bit of max near the Catskills, also near the Tug Hill Plateau, and some of the higher terrain in Vermont and New Hampshire is kind of being highlighted as well. All right, so another thing we wanted to do was to cluster on QPF objects. So as I mentioned, areas of heavy precipitation can straddle multiple geographic regions, so it makes more sense to cluster on objects instead of arbitrary regions. So what we did is we developed an algorithm to identify QPF objects. So basically what the algorithm does is it analyzes the multimodel ensemble mean QPF field and picks out contiguous areas of QPF of greater than 1/10 of an inch. And then the algorithm checks the size of the area and rejects areas that are smaller than about 25,000 miles. Because we just kind of decided that for smaller scale areas, you can have, you know, a decent sized area that's a greater than 1/10 of an inch, but maybe the max QPF in that area is only 1/4 of an inch, which isn't, you know, something that we're maybe concerned about. So we're really trying to pick out the larger areas of heavy precipitation. And then the clustering algorithm continues as before, but only on the area identified by the QPF object. Another thing we wanted to do was add 2-day QPF and QPF percentiles. Again, heavy precipitation events can span multiple days, so we wanted to add 2-day QPF so forecasters can assess the uncertainty for a whole event rather than having to look at 2 sets of clusters for one event. And also we wanted to switch from showing the mean of each cluster to the percentiles for each cluster. So we wanted to show the 10th, 25th, 50th, 75th, 90th, and 95th percentile for the members that comprise that cluster, instead of just looking at the mean of those members that comprise that cluster. All right, so we're just going to quickly go through an example, and this is 2-day clustering with the NBM QMD QPF, and this is for that event that ended on the 48-hour period at 12Z on Saturday, September 5th of 2022. Here's the analysis, the CCPA QPE. We can see that there was kind of 2 areas of heavy precipitation, one over the southeastern US with, you know, pretty heavy, probably convectively driven precipitation, and then another area of heavy precipitation that kind of fell along the Ohio River Valley into Pennsylvania and then further northeast into the New England states. All right, so the clustering continues as before, but now we're looking at, instead of just an arbitrary, you know, northeast, southeast domain, we're actually looking at a QPF object. So we're considering the uncertainty for the whole QPF field. So again, and this is also a 48-hour QPF event. So looking at EOF1, we can see that there's a lot of lower values kind of on the western periphery of this precipitation shield. Some higher values a little bit further to the east, but since this isn't really a dipole, it's mainly a monopole, we're going to say that this first EOF is mainly uncertainty in the magnitude of precipitation. It's also a little bit in the location, but it's mainly uncertainty in the magnitude. Looking at the second EOF, it's more of a dipole, so we're going to say that this is uncertainty in the location of the axis of the heavy precipitation event, but it's also a little bit contains uncertainty in the magnitude, as we can see that, at least for the higher values, they tend to be, you know, the EOF for the positive values is a bit more intense than it is for the negative values. So again, it's uncertainty in the location, but it also is probably a bit of the uncertainty in the magnitude. And oftentimes that's the case. It's like we have EOFs that aren't necessarily strictly magnitude or strictly location. They can be a combination of both. All right, so again, we have the phase space here with all ensemble members, and we went through and clustered it, and I've just kind of gone through with the physical interpretation of each side of the phase space. So again, the members with the positive principal component for EOF1 have less precipitation, negative principal component for EOF1 more, and then negative principal component for EOF2 further northwest with that axis versus further southeast for these ensemble members up in this area of the phase space. So we got 3 clusters when we ran our k-means clustering algorithm. And just looking at the phase space, we can see cluster 1 is kind of down in this part of the phase space. So these clusters, or these ensemble members, have more precipitation with an axis further southeast. Cluster 2, less precipitation in general, because it's mainly in this area of the phase space. And then cluster 3, more precipitation with an axis located further to the northwest. And again, this all will become readily apparent when you actually view the clusters. So looking at cluster 1, which again, if we look at the top here, had 42 of the ensemble members, we can indeed see that there was more QPF and it was located further to the northwest. We can see that axis of heavy rainfall, we have the area in the southeast, but this axis of heavy rainfall is kind of stretching from southern Tennessee into Ohio and into western New York and northern New York. Looking at cluster 2, generally less QPF in general. And then finally, cluster 3, more QPF and located further southeast with that axis of heavy precipitation. So again, we get that heavy precipitation in the southeast, and then that secondary axis is located, from the Ohio River Valley into the mid-Atlantic states and then into New England, which if we compare to the CCPA analysis, cluster 3 was fairly close to what actually occurred. Yes, it was a little overzealous with the coverage of the heavy precipitation in the southeast, but it really did quite well with that axis of heavy precipitation going into the northeast and the mid-Atlantic states, which again, even though this was, relatively speaking, the cluster with the least number of ensemble members in it, it was still good to see the variability in the ensemble. And even though this maybe wasn't the most likely solution at the time, it was still plausible, and a forecaster should be aware of it. And then an alternative view to look at this, and what I actually like to look at, is these are plots showing the difference between the multimodel ensemble mean and each cluster forecast. And again, this really kind of highlights how each cluster is different from each other and the multimodel ensemble mean. So again, you can clearly see cluster 1 has more precipitation on the northwestern side of the precipitation shield, less precipitation over the mid-Atlantic states. Cluster 2, indeed, pretty much less QPF across the board, except maybe a little bit of higher amounts, but mainly offshore. And then cluster 3, more QPF, but the heaviest axis of precipitation is located a bit further southeast. So you can see it's mainly trimming back values along the northern fringes of that precipitation shield. So the last thing we wanted to do was host these tools on a publicly accessible website, and that's what we have done. So the QPF cluster website is basically similar to our general day 3 to 7 cluster website. Instead of day 3 to 7, it's just QPF clusters and then that view.php. So basically, why don't I pause there and I'll take any questions or comments. And then if we have time, we can maybe look at some of the real-time data on the websites.
Looks like we have some questions. Andy, go ahead.
Yeah, Bill, thanks for presenting. And one of those images back, where you're playing with IDA and the track and I love how you pointed out that that majority solution, which actually had like 84% of the European ensemble, and a huge chunk of the GEFS ensemble as well, was the one that actually didn't verify. And I think that goes to the point of, communicating that alternative scenarios that can happen. And that's what I love about the cluster analysis, is it's going to give you a lot of different scenarios that could happen. And obviously, if all the clusters are pretty close together, then maybe there's a little more certainty if you're assuming that the ensembles are dispersive enough. But again, this is what I love about the cluster analysis. It's a great starting point to look at the forecast, unveil the MBM, and see what all the different scenarios are.
Yes, I would agree. And also that's another comment to why this is more useful than, say, looking at the ensemble mean, because the ensemble mean in that case probably would have looked like that cluster with 84% of the European and most of the gaps.
Any other questions for Bill? If not, I have one myself. Okay, so you mentioned a lot of the upcoming things that are being worked on right now. What would you say is coming first down the pipeline that can be expected as far as into the tool itself, like in the near term now?
For the QPF clustering?
Yeah.
Or the clustering in general?
Either, whatever's coming first, I guess. Yeah.
Okay, so, well, actually, with the general day 3 to 7 clustering, I've been working recently with a team from Western region, and we're basically coming up with a new interface to kind of view the clusters that will be a lot more customizable and allow forecasters to dig a lot more into the detail. I don't have an exact date on when that will become available, but that's kind of the big thing and why we've kind of held off on doing a lot of updates to my current cluster website, because we have a much better one that's coming down the pipeline.
That'd be great. The one thing that stands out to me is the customization feature, because I made some other students can comment on this as well, but one thing I've heard over time is that a lot of people will be wanting to look more and more into the detail. Where what are we looking at? So having that customization should also help the pull back the curtain on those details. You mentioned also so that's the overall clustering technique. What about like anything else as far as the other component part of this is being updated moving forward?
Yeah, so we have that newer website that will be coming along, but a lot of the work that I've been doing recently is trying to answer more of like the science questions, because right now obviously we have at least for the day 3 to 7 clusters, we have the CONUS domain and then the 3 regional domains, just trying to establish like what is the ideal domain size. And obviously everything is based on, at least for the day 3 to 7 clusters, everything is based on the 500 millibar heights. We've also started to investigate whether clustering on other variables is better. So obviously you can look at the maximum temperature forecast that's based on those EOFs of 500 millibar heights. But if what you're really after is like, what are the maximum temperature scenarios, maybe it's better that we just cluster directly on that variable. And again, that's something, if we find that's useful, it's going to be rolled out into that bigger website that's coming down the road.
Awesome, thank you. Yes, Andy.
Sorry to ask a question about, you're still running all this at WPC, right? Yeah.
Right, yes.
Has there been any discussion about, and I think I remember a couple of years ago, was question marks of, is it, how operational is it? Has there been discussions about moving this, up to WCOS at all and getting it on there?
No, so we haven't gotten that far yet. I think the more grassroots support it gets, it could definitely go in that direction. But yes, right now there isn't really plans to make it more, to the level of WCOS. But right now it is fairly stable. It's just, if we have, network issues that are outside of our control, then it's just obviously not going to happen. But it's pretty stable most of the time.
Cool. I have one more question, but I'll let Rosemary go.
Rose, you have the floor.
Thanks. This has been really interesting. And you mentioned that you're a ways away from anything that's operational, certainly, and mentioned unless you get grassroots approval. What do you mean by that exactly?
Just mean like grassroots support. So like this whole project was a grassroots effort. It was never funded. It was just something that I started working on as a side project, and it basically snowballed from there. So like the more people asking for it to be, you know, more stable and more operational, the more likely that's going to happen, basically. The more people that are advocating for it, it's more likely to get the attention of the higher ups who make those decisions, basically, is what I was trying to say.
Okay, they're advocating in terms, in essence, saying this could be really useful in the forecast process.
Right.
Okay, thanks.
Hey, Andy, you have one more question? Yes?
Yeah. Talk about advocating the forecast process. It's like for me, like, man, I wish I was back in the field because I would put this like as my like first thing I would look at almost every day and start here because this is going to give you the range. I had shared around to our students this for late last week a nice example where the cluster analysis really unveiled like comparing that to like the max T standard deviation. We were talking max T earlier, that you can see the differences in the max T fields in the clusters and then the max T standard deviation, the MBM, and the two are very much linked. And it snowballed down a different route of discussing about, do forecasters need to understand the whys of, why are some of these clusters doing what they're doing? Why do you have, and is that knowledge needed, or is it from a, is it better from a communication perspective just to say, hey, like take example here, Ida one, why is the majority slower? Why are the others faster? Do we need to be able to understand all that? I don't know. I'd just like to hear your comments on it.
So yeah, I totally agree with you. And right now we have a proposal in to sort of address some of those issues. So basically there's another data analysis technique that's called Ensemble sensitivity. And basically what that can do is answer those questions, is basically say like, why is this cluster behaving the way it does? Like what earlier in the forecast is happening that is causing that? So right now we have a proposal in to get funding to work on that and basically to link that together with the clusters, but we'll see if that actually gets funded or not. But yes, I totally agree that that's something that's important and needs to be addressed. And we would like to work on it. And we have a way that we think we can tackle that.
All right. Thanks, Andy. And thanks, Rose, for your question as well. Steve, you're up.
Hey, Bill, thanks for the presentation. If you go back a couple of slides, I think it was the last case you were showing, like you had a 4-panel. Yeah, but go forward one. Yeah, that one. So I guess, as a forecaster, you've got the two clusters on top that are, kind of dry. I mean, it almost covers the whole gambit there. If I'm in the mid-Atlantic, I'm either dry in the upper left, I'm neutral in the upper right, and then I'm wet in the lower left. So how would you tell a forecaster, how should they use this?
So we're advising people that it's mainly for like situational awareness, because obviously picking the right cluster can be challenging. It's no easier than picking the right, deterministic forecast or something like that. So we kind of use it as like a situational awareness. So basically, like say cluster one, it's probably, in this case, it didn't end up verifying, but it's the most likely solution, which is a bit drier. But also cluster three is, just for communicating to partners, there is a scenario where, we could get, 2 or 3 inches of rain or something like that. And it's just mainly for situational awareness and kind of communicating to partners that maybe want that, uncertainty information, to be able to give them that uncertainty information.
Right, and I agree with that wholeheartedly. I guess in this case, it really looked like cluster 2 didn't do all that great. I'd be hard pressed to say which one of these was the best, in the end, compared to what happened. So I mean, there's always that uncertainty, and with the models and the resolutions that we run right now, you see this day in and day out. So I guess I'm just struggling, how much this adds to our arsenal of, evaluating guidance.
Right. And one thing I will add is, like, obviously we are simplifying the ensemble down, but we only got, in this case, 3 clusters. If you're trying to, get one cluster that's going to be super correct, then maybe we should break this down into like 6 clusters or 7 clusters. But, it comes with a trade-off. Like, again, that's more information that someone has to look at. And stuff like that. So again, this is probably maybe like an oversimplification in this particular example of the range of possible forecast scenarios, but it just comes down to, what are you prioritizing? Do you just want a brief overview of what the possible scenarios are, or do you want to go, more detail, but obviously not as much detail as looking at all 100 ensemble members, basically.
Right. Okay. Thanks.
Yeah, I'm just gonna add a comment, I guess, and correct me if I'm wrong, Bill, but basically, if hypothetically you were to create additional clusters, it would be really creating more noise effectively, because you'd be seeing a lot more of the noise in the distribution.
Yeah, so basically, yes, you'll end up with one cluster that probably does really well, but you'll also end up with several more that do terribly. And it's like, again, it's, signal versus noise. I would kind of agree with you on that. So these are like the overarching different scenarios, but obviously it's not going to capture 100% of the variability.
Yep. Signal interpretation. Yep.
Right.
Okay. Really good conversation. Any other questions for Bill before we progress, time allowing, into additional demos here? Are going once, going twice. All right, back to you, Bill. Thanks.
Okay. So yeah, so why don't we just take a peek at the website so you can kind of see what it looks like and how it operates. So this is our QPF clustering website, which is pretty new, only came out with this maybe like a few weeks ago, but basically it's set up similar to our day 3 clustering website, but you can click here and you can look at days 1 through 6, or you can look at, again, those 2-day totals for days 1 to 2, 2 to 3, 3 to 4, 4 to 5, and 5 to 6. Here, since we're looking at QPF objects, here are the 4 different objects. Now we have it default to 4. Most days there's only like 1 or 2 objects. So if you say, go to object 3 and it isn't an object 3, it'll just say no object found. But at least for day 6, we do have an object for object 1, and that's over the Eastern US. Again, we're looking at the 2 EOFs here. So again, for this particular case, which is about in the middle of next week, we can see for that EOF 1 here, it's probably an east-west shift. But there's also some sort of magnitude. Like I said, a lot of times an EOF isn't strictly magnitude or isn't strictly, a shifting in the location. It can be a combination of both. So in this case, it's an east-west shift, but it's also a little bit of magnitude. Whereas EOF 2 here is mainly a magnitude here, because we can see that we mainly have a monopool that's aligned with the axis of heaviest rainfall. So that's the EOFs. And then again, you can look at the phase space, and then when you get down to the cluster percentile QPF, that's when this thing will become active. And then you can toggle down. This is just the 50th percentile, but you can say, look at the 10th percentile. So probably, expect at least this much. And then we also have some of the higher percentiles as well. So again, you can look at, like, say, the 90th percentile. And that will show you the 90th percentile as calculated from the members that comprise each of those 3 clusters. So it's basically set up to default to that 50th percentile, because again, treating that as sort of like, most likely. And then these are the 3 different scenarios. And then we have the same thing for the percentile difference for the QPF. Again, you can toggle through and look at the difference from the ensemble, from the multi-model ensemble for the different percentiles, basically. So did anyone have any questions on that?
Yeah, Jeff,
Yeah.
go ahead.
Yeah, Bill, the percentiles calculated the same way using the binormal?
No, so these are just raw percentiles from the constituent members that comprise that cluster. That's a good question.
Thanks.
Any other questions before pushing forward? Okay, hearing none.
Okay, so yeah, so that's basically the new QPF clustering website. And then I'll just quickly look at the day 3 to 7 clusters just in case anyone on this call was not familiar with them. So here's our day 3 to 7 cluster prototype page. So it's basically the same methodology that we use as for the QPF clusters, except we are applying it to the 500 millibar height forecast over that particular day. So I have it defaulted here to day 7 over the eastern US because it looks like there could be some interesting weather as we get to the middle of next week. So what we have here again are the EOFs, but this time again we're looking at the height field. This first EOF is basically kind of east-west shifts in this location of this cutoff upper level low. And then EOF2 is more kind of amplitude differences, maybe the location, you know, the north-south location of that upper level low. And again, the extent of the downstream ridging. So like with the QPF clusters, we go through and we cluster the ensemble members based on this PC1, PC2 phase space. The one thing I will say is that for the day 3 to 7 clusters, right now we are defaulting to 4 clusters. That will probably be changing when we roll out that more expanded website with more customizable stuff. But for now, we're just defaulting to 4. There's unlike the QPF clusters where it could be 3 to 5. And then, so quickly just looking at the day 7, these are the height patterns for the 4 clusters. And again, how they differ in this case from the multi-model ensemble mean. And then you can kind of relate this, or what I like to do is sort of relate this to the other fields of interest. Because what we're really interested in is like, you know, the surface parameters, like maximum temperature or QPF. So if we just kind of toggle back and forth between these 2 clusters. So on this page, we have the 500 millibar height forecast and how they differ from the multi-model ensemble. This is the clusters for maximum temperature. So again, the same constituent members for each cluster, but now we're looking at maximum temperature and how it differs from the multi-model ensemble. And a lot of times it physically makes sense. So if we look at cluster 1, it has, you know, some more intense ridging out ahead of that upper level low. No surprise, the maximum temperatures are being forecast to be a bit warmer over the Ohio Valley and western Pennsylvania. Same with cluster 2. It basically has that trough shifted further to the east with lower heights over the eastern US, higher heights over the south central plains. And you know, it kind of works out pretty well is that cooler conditions are being forecasted over the Ohio Valley and into the mid-Atlantic states with warmer temperatures over the south central plains. And same thing with cluster 3. We have more intense ridging kind of building out ahead of the upper level low. And basically the low is kind of shifted a bit further to the southwest. No surprise, warmer temperatures being forecasted where we have that more intense ridging, cooler temperatures under that upper level low, which is being displaced more to the southwest over the central plains. And then same thing for cluster 4, where we have maybe a more intense upper level low that's maybe displaced a little bit further to the north and more intense ridging downstream of that. Cooler conditions over that more are under that more intense upper level low, and then more warming out ahead of it. So that's kind of like the way I like to look at it, and I really like to kind of link what's happening at 500 millibars to what's happening at the surface, and oftentimes they match up pretty well. So did anyone have any questions on like the day 3 to 7?
Yeah, Reed, go ahead.
Okay, thank you. This website and the other one you just showed, I see there's like 31 days of data available. Are you going to limit the range of data that's available? So if we want to go back like 5 weeks to look at something come up in April, just talk about, is that going to be available, or are you just going to keep it like 30 days running total?
So right now we have it capped at 30 days. We could possibly expand that. So right now, at least at WPC, we're in the process of transitioning all our web stuff over to Amazon Web Services, which basically gives us unlimited storage. So right now we don't have unlimited storage, and that's kind of why I'm limiting it to 30 days. But once we actually make that transition to Amazon Web Services, which I have no idea when that's going to happen because it was supposed to happen last week and then it didn't happen. But when that actually happens, we could expand that archive back to maybe, like 2 or 3 months or something like that.
Okay, thank you, Bill. Appreciate that.
Thanks, Reed. And Jeff, go ahead.
Hey, Bill, the new page that you referenced, is that the DESI?
Yes,
Yeah.
the DESI page that we're working on.
For everyone else on the call, I've been fortunate to see a little demo of the DESI, and it's most exciting. It was initially developed by Travis Wilson, who did the 1D viewer. And I think we're looking to maybe do a webinar on that as we get later into the spring, and it's getting closer to being rolled out. So I believe that, they're in the effort of transitioning that over onto the cloud, and that'll enable it to be opened up to everyone out in the field. So very exciting in terms of trying to support basically more of a quantitative IDSS, being able to communicate more specifically the types of scenarios that might be possible to our partners to enhance their decision-making capabilities. So something to really look forward to. Travis did a presentation at AMS. I believe it was Travis on DESI, and there'll be more coming out in the coming months.
All right. Thanks for that note, Jeff. Definitely looking forward to getting that organized. Any other questions this morning for Bill?
Not as much a question, but a comment. I just want to say I appreciate the presentation. It's the more times I see it, the more information I'm able to glean from it, and I'm excited to kind of see where it goes.
Thank you.
Yeah, I'd like to echo that comment. The more I think the theme is repeated exposure, right? The more we see it, the more we understand it, the more we're able to use it more effectively. So this is really good. The explanation, of course, as mentioned at the beginning, getting some more kudos in chat here. This is a great tool, and we'll get this uploaded to the Eastern Region SSD forecasting tools page as well. Shortly after, this webinar is also recorded for all those that could not attend, and we'll get that uploaded to the Eastern Region Science Sharing page later today. Jeff, any other final thoughts from your end?
No, just thanks again, Bill. I think for an excellent presentation and a very useful tool.
Thank you. And I will say I'm meeting on Monday with someone, I forget their exact title, but they're in charge of putting together more formalized training for various tools in the Weather Service. So hopefully we can come up with some more formalized training as well, because obviously it's just been sort of these, one-off webinars here and there. So.
Great.
Awesome. All right. Well, again, thank you, Bill, and more kudos coming in chat. So, and I'm sure you'll get more and more, especially also when that training comes along, since that'll help to integrate this into operations, frankly. So, if nothing else, thank you, and hope everyone has a smooth rest of your day today with the severe weather threat as well.
Yes.